Sorry. Now we are turning to chapter 3 about the orthogonality. So what is okay? As you know well, being orthogonal means two lines are intersecting at 90-degree angle. So okay, and I want to translate the notion of the orthogonality in the world of linear algebra. So in order to do that, so I will need to begin from the notion of the inner product and the length. So what is the inner product? I think I have already introduced the inner product. So inner product of two vectors, so x and y, is nothing but x transpose and y. So this is basically component-wise multiplication and taking summation. Now, and length. Length is also easy. So due to the Pythagorean theorem, so we define length like this. So if x is any random vector from Rn, then we square every component and take the summation and take the square root. So this is the length. Inner product and the length. And well, also length can be understood as taking the inner product of itself and x and itself and take the square root. So this is also again the length of the vector. Now, inner product and the angle, they are very closely related. This can be easily seen by looking at the law of cosines. And law of cosine can be applied to two-dimensional space and the three-dimensional space. So I will begin from there. For any vectors, for any plane vectors or for any three-dimensional vector x and y, the inner product of the inner product of x and y is the same as the length of x times length of y times cosine theta. Here, theta is the angle between x and y. Okay. Okay. So what is the law of cosine? So according to the law of cosine, well, so length of this guy squared plus length of that guy squared minus 2 times length of this guy times length of that guy times cosine of this one. It's going to be the same as the square of the length of this left side. Okay, so that was the law of cosine. Okay, let us keep this in our mind. This is my vector x, and this is my vector y. So this is x and this is y. And this point is the origin. Now I can consider this left side, left vector, as x minus y, right? X minus y is not precisely this vector, which should be originating from the origin. Well, but if you parallel translate this vector, then well maybe this guy can be understood as x minus y. Then, sorry. I want to find the square of the length of the lead one. But this one can be computed by taking inner product of x minus y and x minus y. And also, the inner product is, everything is linear. Therefore, this inner product is the same as inner product of this and that, this and this, and this and this, and this and that. So, which consists of 4 terms. So, x inner product with x is x squared minus x transpose y minus y transpose x plus length of y squared. But inner product is commutative. So x transpose y is the same as the y transpose x. So x minus 2 times x transpose y plus y squared. And on the other hand, because of the law of cosine, x minus y length squared is the length of x squared plus length of y squared minus 2 times length of x, length of y, and cosine of theta. So, so those two numbers, x squared and y squared, they both cancel out each other. And so x transpose y is x, y, and cosine theta. Okay, this is very good to know. So if there's anyone in this classroom who have never heard about this formula, then, well, maybe this is the right time to memorize this. Okay. However, I proved the theorem just by using the law of cosine, but we are not pretty sure that if the law of cosine is true for high dimensional vector spaces. So in order to define the notion of angle in higher dimensional Euclidean space, then there is no other way but taking this last equality as our definition. So in higher dimension, we define the angle like this. Choose any 2 vectors from Rn. This time around, so n may be greater than 3. So this one can be 4 or 5 or whatsoever. Then the angle is defined like this. The angle theta between x and y is defined by the following formula. Cosine theta is x transpose y divided by x and so well, this equation is nothing but solving this equation for cosine theta. In order to justify this definition, I will need to show that this number is always a number between -1 and +1. How do I know that? Well, there are many explanations, but well, the easiest explanation may be, have you ever heard about the Cauchy-Schwarz inequalities? Yes. Yeah. So if you understand Cauchy-Schwarz inequality, then absolute value of this guy is always less than equals to absolute value of this guy. Okay. So therefore, that number must be always between -1 and +1. So then therefore also because of the reason, so there can be only one unique data in this range satisfying this equality. So that now we are taking that data as our definition of the angle for the higher dimensional vector spaces. Okay. Now we are mainly interested in 90-degree angles. And so if the data is just 90 degrees, if the data is pi over 2, then cosine of pi over 2 equals to 0. So, because of the reason, so we say two vectors are orthogonal or perpendicular to each other if their inner product equals to 0. We say two vectors x and y are orthogonal if their inner product is 0. Okay, now we know the notion of the definition of the orthogonality. And okay. And if suppose that you have two orthogonal vectors, then and our visual intuition says that these two vectors should be linearly independent. Okay, so what about you are working on n-dimensional Euclidean space, and suppose that you have chosen some k orthogonal vectors, then can I say they are always linearly independent? Yes, that is also true. This next theorem says that if you can find any set of mutually orthogonal non-zero vectors in Rn, then they are automatically linearly independent. Suppose that I have chosen k vectors in Rn. They are all non-zero vectors. And let me say they are mutually orthogonal. Mutually orthogonal, I mean by if you take any pair of vectors from here, and if you take the inner product, then it's going to be 0. So this condition is what I mean by the mutually orthogonal. So I have such k vectors from V1 to Vk. Then these vectors are linearly independent. All right, I want to prove this. Since we try to prove some certain set of vectors are linearly independent, so we need to consider this vector equation. Ck Vk is 0. And if I can show that all these coefficients equals to 0, then that means these vectors are linearly independent. How? We take the inner product with Vj and this vector. Then, since this guy was assumed to be 0 vector, and taking inner product with 0 vector is automatically 0. And on the other hand, the inner product is always linear. So inner product with this guy with that vector is the same as inner product of this one with that plus this one with that, da da da, and plus this one with the last one. But because of the mutual orthogonality, almost everything vanishes, but the ith one, jth one, the only this guy survives. Right? So this means the Cj times the length of Vj square equals to 0, right? This guy equals to 0 means that this one equals to 0. But here we are assuming that all vectors are non-zero vectors. Therefore, their case, so Vj square cannot be 0. So Cj must be 0. And this is true for 1, 2. Okay. So therefore, these vectors are linearly independent. Okay. So if you can find some mutually orthogonal vectors, then they are very well from time to time. So they are very convenient because because being also mutually orthogonal means that if you take the inner product, then almost everything vanishes 0, but only one. So therefore, and also being mutually orthogonal means that they are automatically linearly independent. So it is very advantageous to find the mutually orthogonal basis for any given vector space. So this is the definition. Suppose that these basis vectors, so I am working on the vector space Rn, and if my basis vectors are mutually orthogonal, then because of the theorem, then they are automatically linearly independent. Then we say it is an orthogonal basis. So they are all, and on top of that, if all those vectors are unit vectors, length equals to 1, then we say these vectors are also normal basis. So normal, I mean by length equals to 1. So we can always find the orthogonal basis, also normal basis. The easiest example of the orthonormal basis is the standard basis. So do you remember in our previous lecture that we worked on the standard basis? So we actually express any given linear transformation in terms of the standard basis. And I really like the standard basis because their lengths are all equals to 1 and they are mutually orthogonal. The standard basis is very typical example of orthonormal basis. The standard basis E12 En is an orthonormal basis and also we talked about this basis system. So do you remember this? So when you try to figure out the matrix for the projection and reflection, we have been working on this basis. Was it? Yeah, minus sine and cosine. And these are all length 1 and they are orthogonal to each other. So this is also an orthonormal basis for R2. R2. Okay, easy. Do you remember? So do you remember what I meant by the two spaces are orthogonal? Oops, sorry. Sorry, I messed up. So it has to be. What I meant by two subspaces are orthogonal. That means you have a huge ambient vector space, and suppose that you have two different subspaces in that ambient vector space. And these two vector subspaces are orthogonal to each other was defined by every vector in the first subspace was perpendicular to all the other vectors in the second vector space. If that was true, then we said those two subspaces are orthogonal to each other. Okay. I have two subspaces of ambient vector space V. These are subspaces of V. We say these two subspaces are orthogonal if the inner product of V and W is equals to 0 for all right. So this is our definition of two subspaces are orthogonal. From time to time, so this orthogonality of two subspaces are sometimes counterintuitive of our visual, counterintuitive. So if you're especially if you rely on the visual intuition. So I just came up with this example. So these two vector space S and T, they are subspaces of R3. And well, visually, the first vector, the S is nothing but the XY plane. And T is, what is that? YZ plane. Yeah, so the first one is this, and the second one is that. And well, our visual intuition says that those two subspaces should be orthogonal to each other. But is it true? No, they are not orthogonal. Even though they look like orthogonal, but this guy is clearly not orthogonal to this basis vector. Okay, so those two guys are not orthogonal. What if I change my question like this? If I drop if I drop E2, then are they orthogonal? What do you think? Yeah, this time they are orthogonal subspaces. So these are orthogonal subspaces. And there is also a very important example of orthogonal subspaces. These are the so-called four fundamental subspaces of a matrix. I just ran out of space. I have an n by n matrix A, and So we were able to define these four fundamental subspaces: the column space and null space, row space and left null space. And this guy is the subspace of Rm, and this is subspace of Rn, Rn, and Rm. So it looks like the column space and the left null space, they belong to the same ambient space Rm. And so, and likewise, the null space and the row space, those two also belong to the same ambient space Rn. And yeah, I just want to group these two and that two. And well, if you're remembering my previous lecture from the last week, I don't know, I forgot. And this guy was orthogonal to the column space was orthogonal to the left null space, and the null space was orthogonal to the row space, right? So if you choose any random guy from this one, then that should be orthogonal to every other guy in the row space, and so on. And also, I spelled out the dimensions of each of these vector spaces. Now, orthogonal complement. Let me say that I have chosen some vector space V from Rn. And I want to define the orthogonal complement. We use this symbol just to represent the orthogonal complement. Yeah, this is somehow very strange symbol appears here. This looks like an inverted T, but this is not T. So this symbol represents the perpendicular orthogonality. So, and we read this symbol by V perf. V perp. Obviously, the perp is short for the perpendicular. Okay. So what is V perp? What is the orthogonal complement of V? Which is the set of all vectors in Rn which are orthogonal to every vector in V. So these are like collection of all such vectors. Then we say that's so V perf is again the subset. So a priori, V may not be a subspace. V is just some random subset of Rn. And we say that it's an orthogonal complement. Now, this theorem tells us some very important properties of the orthogonal complement. This theorem consists of the five propositions. The first proposition is the V perp is again a subspace. So V perp is not just a random subset of Rn, but this actually is, this guy is also closed under vector addition and the scalar multiplication. And and if you take the intersection of the V and is orthogonal complement, then it has only one element, zero vector. And if the vector space V is a k-dimensional subspace, then its orthogonal complement is n minus k. So this n is, well, clearly this n means the dimension of the ambient vector space. So that means, well, vector space V and V perf, their complementary dimensional subspace of contained in Rn, right? So by now, if you remember anything from my last lecture, then condition number 2 and condition number 3 reminds me of the direct sum, right? So suppose that you have a huge ambient vector space, and if you have two subspace of that ambient space, and if these two spaces, they only intersect at the origin, and if those two guys are complementary dimensional vector spaces, then we say this huge ambient vector space can be written as a direct sum of these two subspaces. You remember this? Yeah. So if you understand that, then clearly condition number 2 and 3 says that V and V perf is always a direct summand of the ambient vector space Rn. Okay. All right. So, but however, anyhow, so if you do not remember anything about the direct sum, that is okay. Okay. Because today I will explain one more time. And number 4 is for any vector from the ambient vector space X, then X can be uniquely written as a sum of vector in V and another vector in its orthogonal complement. And lastly, if you take the orthogonal complement of the orthogonal complement, if you take the orthogonal complement twice, then what would you expect? Then that is going to be your original vector space V. All right. So today I will try to prove all these 5 statements, propositions. Yeah. 그냥 set theoretical, if you're just taking the set theoretical union, then no, you cannot get the Rn.
그러면 저거를 V에 대한 orthogonal complement라고 부르는 게 아니라 orthogonal 따고만 하는 게 직관적으로 맞지 않나요?
아, 좋아요. 좋은 지적인데요. 자, 우리 그러니까 예를 들어서 3차원에서 suppose that this is your vector subspace V, then its orthogonal complement is what? 이거죠, 그렇죠? 그러니까 얘랑 set theoretical union을 취하면은 여기 있는 친구들은 우리가 없잖아요, 그렇지? 그러니까 이건 사실 as a set theory, union of 뭐지? 이거랑 이거 아니 이거는 일반적으로 이게 아니게 되겠죠, 그렇죠? 그렇지만 이건 어때요? 이거는 이게 되겠죠, 그렇죠? 맞아요, 좋은 지적이에요. 그러니까 so even though I use not me. So even though Professor Strang he persists to use the terminology of the complement, then yeah, good point. So this is not set theoretical complement. So it has clearly another meaning. Okay, yeah. Okay. Number one, V-perf is a subspace. This is easy. Choose any two vectors from V-perf. Then for any vector in V, the inner product of V and X and W and X must be 0 because they were chosen from the orthogonal complement of V. So it suffices to show that the any linear combination of V and W must be the member of the orthogonal complement. But this is also again very easy. Since those two guys equals to 0, so therefore this one has to be 0 too. For any real numbers C and D. So therefore this guy is again orthogonal to every member of vector space V. So therefore its linear combination must be the member of its orthogonal complement. Therefore this space is closed under addition and scalar multiplication. Okay. All right. And number two. What is number two? Yeah. Suppose I have chosen any vector from intersection of the V and its orthogonal complement. Then at the same time, V is a member of V and V is the member of its orthogonal complement. And well, V as a member of the orthogonal complement of V, therefore V must be orthogonal to every vector that is in the vector space V. That means V taking inner product with itself has to be 0. Okay. In other words, the length of V has to be 0, and there is only one vector whose length equals to 0, which is the 0 vector. Okay. All right, and number three. So I am supposed to show that V and V-perf, they are complementary dimensional vector space. And hey, what was our definition of the dimension of some vector space? So definition was the dimension was given by the number of basis vectors. Okay, so I will need to show that if there is k basis vectors for original vector space B, then I must be able to find precisely n minus k vector basis vector for its orthogonal complement. Okay. I have, so these are, let me say, these are the bases of V, and also I will say these are bases of its orthogonal complement. And I need to show that I have precisely n minus k such vectors, which means, in other words, I have to show that this index m must be n. If m equals to n, then that means I have precisely n minus k vectors here underneath. Okay. So we will show m equals n. How? First, I will show you that m is less than equals to n. To show this, let me take a union of these vectors and that vectors. Then I have this many vectors. I have precisely m vectors. And if I can show these vectors or these vectors are all linearly dependent, then, and you know, these vectors are the members of Rn, right? The M, which is the ambient vector space. And in Rn, the number of linearly independent vectors cannot exceed dimension of n, right? So that means if I can show all these vectors are linearly independent, then m, that implies that m must be less than equals to n, okay? So these are linearly independent. Because C k plus 1, V k plus 1, C k, V k. So to show that these are linearly independent, then from this given vector equation, I must be able to show that all these coefficients must be 0. But again, this is easy. If you send all these terms to the right side of this equation, then you will end up with this equality. So this vector equals is that vector. But you know, these vectors from V1 to Vk, they were assumed to be the basis vectors of V. So therefore, this guy must be the member of V. And Vk from Vk plus 1 to V, oh, sorry, not K. I messed up. It has to be M. But these vectors from Vk plus 1 to Vm, they were the basis vectors of the also Vperf. Therefore, this is a base vector in Vperf. So which implies that these two guys, these vectors, they are the member vectors in the intersections of V and V orthogonal complement. But you know, there's only one such vector that lies in the intersection of these two, which is a 0 vector. So this guy equals to 0 and that guy equals to 0. And since V1 to Vk, they were assumed to be linearly independent. So C1 to Ck has to be 0. And also Vk plus 1 to Vm, they were all again assumed linearly independent. So Ck plus 1 to Ck, they all have to be 0. Okay. And Ck plus 1, Cm has to be 0. So they are linearly independent. All right. Now, the other direction. Now, I want to show you that m is greater than n. Right, so m is greater than equals to n. How to prove this? I want to provide contradiction. Suppose not. Let us assume that m is less than n. Okay. Oh, so in order to derive contradiction, I want you to consider this matrix. This is a matrix given by every row of this matrix is just the basis, these basis vectors. So I have m basis vectors here and there. I have just all these vectors. I have m vectors, and this matrix consists of the row of this matrix consists of these basis vectors from 1 to m. Okay. And also, I want to emphasize that each of these rows, they are the member of Rn, right? So that means the number of rows is m, and number of column equals to n. So this is m by n matrix. So, and because of this assumption, this matrix must be not narrow matrix, but this is a wide matrix. Okay. Is an m by n matrix. Okay, so this is an m by, this is a wide matrix. And do you remember this? That wide matrix cannot have trivial null space. If your matrix is wide matrix, then null space of that matrix must contain some non-zero vector, always. No? Okay. 컬럼들이 디펜던트할 수밖에 없다는 거죠. Right. Okay, so since m is less than n, the null space of A cannot be trivial subspace. So this means there is some non-zero vector, which I will call C, in N of A, null space of A. All right. Now, okay. So A times C is 0. Oh, okay. All right. Okay. I was confused a little bit. Sorry. So A multiplied by this column vector C must be 0 vector. Okay, because this guy is obviously the member of the null space. Now, so this is basically you are multiplying this column vector C on the right of this matrix, and multiplication of this guy equals to 0 means Vi or I. So this guy equals to 0 means the taking, and then every column, every entry of this 0 vector is actually nothing but the inner product of this row by this column, right? So, is it a contradiction? Oh yeah, this is clearly contradiction. So let me just go back to here. So that means this is, I was able to find some non-zero vector C such that this C is orthogonal to every basis vectors of vector space B, and this guy is again orthogonal to every basis vectors of the orthogonal complement of B. Okay. So since C is orthogonal to every basis vector of B, that means B must be the member of V perf, right? And C was orthogonal to every basis vectors of V perf, right? That means C is a member of V perf and perf, right? Right? But however, if you believe in the statement number 2, for any subspace, the space and the subspace and its orthogonal complement only shares the 0 vector only. So this implies, and clearly this C lies in the intersection of V perf and V perf perf. Has to be zero vector, which is a contradiction. Okay. Where was I? Okay, all right. And number 4. And what was number 4? Oh, every x can be uniquely written as a sum of vector v and vector in v perf. Okay, this is clearly true because, which is obvious, because v1 to vk and vk plus 1 to vm. Oh, no, not vm. Now I am safe to say the index ends at n, right? So these are assumed to be basis of v, and these are the basis of the v perf. And union of all these vectors, there is I can say these are basis of Rn. So theorem is proved. So therefore, every vector in this space can be written as a linear combination of this. And if you take this part, then this is a member of V. And if you take that part, then that's going to be the member of the V perf. Okay. So claim is done. And the last proposition is about taking the orthogonal complement twice. Okay. So I have very interesting argument to prove the number 5. Just choose any vector from original vector space B. And we are assuming that this is k-dimensional vector space. Then we taking inner product of V and any random vector W from V perf must be 0 because V perf was the orthogonal complement of V. Then that means V is orthogonal to all vectors in V perf. Okay, then that means V is a member of, so V is orthogonal to every vector in this space. Therefore, V must be the member of V perf and perf. Okay, it's kind of getting tricky. But if you remember the definition of the orthogonal complement, then you know what I mean. Okay, and here so I have just chosen any random vector from V, and this random vector turns out to be the member of this guy, so belongs to this guy. So V is a subspace of V perf and perf. Okay. Now, this is n minus k dimensional vector space, okay, right? Then V perf and perf is the, ambient vector space is always Rn. So n minus k, which is k dimensional vector space. All right. So, so V perf and perf is k dimensional vector space. Okay. And also we already assumed that V is again k dimensional vector space. So this is the scenario. So I have this k dimensional vector space is contained in another k dimensional vector space. Then only possible explanation is this guy is precisely that guy. Okay. So if you have the vector space, and if the vector space contains another subspace whose dimension is the same as the ambient vector space, then the subspace must be the same as the ambient vector space. That is the idea. Okay. Okay, all right. So this is the orthogonal complement. So being orthogonal complement is a very strict condition. So in order to be, so if suppose that you have two vector spaces of some ambient vector space, then if being these two guys are these two guys being the orthogonal complement to each other means first those two guys, so those guys must be the sum end of the direct sum. So the ambient vector space must be can be written as the direct sum of these two guys. On top of that, these two guys also must be the orthogonal to each other. If those two conditions are satisfied at the same time, in that case, you can only say those two guys are orthogonal complement to each other. So very strict condition. Let me find the orthogonal complement of span of 1, 0, 0, 0. And 0, 1, 0, 0. All right. Can you figure out is orthogonal complement? In this case, I think this is very easy, doable, right? Because, well, this space is in the 4-dimensional vector space, and clearly, this space is 2-dimensional subspace of the 4-dimensional Euclidean space. Therefore, its orthogonal complement must be also 2-dimensional, and that orthogonal complement must be spanned by 0, 0, 1, 0, and 0, 0, 0, and 1. Okay, that was easy. What about this? Now, this subspace is a subspace of R3, and I want to find the orthogonal complement of this space. Here, this is 2-dimensional subspace. Clearly, this is 2-dimensional subspace. Therefore, its orthogonal complement must be 1-dimensional vector space. So therefore, must be spanned by only one vector. Can you find that vector? Yeah, this is somehow tricky. The first thing that comes in my mind is taking the cross product, right? So in 3 dimensions, you can enjoy such a luxury only in dimension 3. So if you take the cross product of 2 vectors, then the resulting vector is automatically orthogonal to these 2 vectors. So this is one way, one option. Or so if you don't feel like to use the cross product, then maybe you can try like this. You know, the orthogonal complement has only one basis vector, which I will call x, y, and z. And since this guy must be orthogonal to this one, and that one at the same time, so I can think of this system of linear equations. So this x, y, and z must satisfy 1 times x plus 2 times y plus 1 times z equals to 0, and 0 times x plus 1 times y plus 1 times z equals to 0. So I was able to obtain a system of 2 equations and 3 unknowns, okay, which is an underdetermined system. And if you can find at least one solution from the system, then that is going to be the basis vector of the orthogonal complement. Okay. All right. Okay, great. But what if if my dimension is getting higher, and if the number of such vectors are increasing, then maybe you might need to think of some another algorithm to find the orthogonal complement. So which I will discuss later. The idea is this. So this is the key theorem in order to discuss such an algorithm, which goes like this. The left-hand side, for any n by n matrix A, the column space and the left null space, both of them, they are the subspaces of Rn, right? Column space and left null space, they are both subspace of Rn. And the theorem says those two guys are actually orthogonal complement vector space. So if you're paying attention, if you have been paying attention to my lecture, then actually I guess you already have guessed this. This is a completely new theorem. They are orthogonal complement. So because we know those two guys are orthogonal subspaces, and also those two guys are the complementary dimensional vector spaces, and they only intersect at the origin. Therefore, yeah, they are also going to complement each other. The column space is a subspace of Rm, and whose dimension is rank of A. Then for any vector in its left null space, this is again the subspace of Rm. The inner product with V and every column of A must be 0, because yeah, that was the left null space, so has to be 0 for every column. And so V must be the member of, since V is orthogonal to every spanning vector of the column space, so V must be the member of the orthogonal complement of the column space, and that means left null space is a subspace of the orthogonal complement of column space. But well, we know this is m minus rank of k dimensional vector space, and since this guy was rank of A dimensional vector space, and we are talking about its orthogonal complement, so this is again m minus rank of k vector space. So this vector space, which has the same dimension as its ambient vector spaces, so therefore these two guys must be the same. Okay. All right. Okay. As a matter of fact, there is a dual theorem for this. What is the dual theorem of this? This theorem is true for any matrix A. Therefore, this theorem has to be true, even though we replace this A by A transpose. What happens if we replace A by its transpose? Then the column space of A transpose, which is the row space of A, is the orthogonal complement of A transpose. But taking two transposes is same as the taking nothing. So this is the dual theorem. So column space is orthogonal complement of the left null space, and the row space is orthogonal complement of the null space. All right. Now, we can summarize this result by namely so-called the fundamental theorem of linear algebra. In any math course, so if you're attending any other math course, and if your professor says some theorem is fundamental, then you should memorize it by at least end of this semester. Yeah, and this is our fundamental theorem of linear algebra. And it goes like this. Well, but the statement itself is very easy. For any given matrix, null space of A is an orthogonal complement of the row space. And okay, which is this. Null space is orthogonal complement of the row space. And the second statement is the left null space, which is this, is the same as orthogonal complement of the column space. Okay. All right. There is a direct consequence of the theorem. You remember the condition for any system of linear equations given, so under what condition can I find the solution of this guy? Well, I can find the solution if and only if the this right-hand side vector is a member of the column space of A. Okay, but column space of A turns out to be orthogonal complement of the left null space. So I can replace this by this guy has a solution if and only if B is orthogonal to every vector in the left null space of A. Okay. Okay. Not a big deal. I'm just paraphrasing every statement in terms of the orthogonal complement. All right. This is the last exercise for today's lecture, and I am supposed to find the left null space of this matrix. And the left null space is orthogonal complement to the column space. Okay, and here that obviously I have 3 columns, so therefore it looks like the column space is 3-dimensional space. But this column space is also a subspace of R3, Therefore, its orthogonal complement must be the trivial vector space. Am I right? No, not exactly. If you take a look at this matrix very carefully, then it turns out you have only 2 linearly independent columns, not 3. Okay, so you have the column space is 2-dimensional vector space contained in R3. Therefore, its left null space must be the 1-dimensional vector space contained in R3, right? So I really like I really like this exercise because I can try to rephrase this exercise like this. Suppose that suppose that 3 random columns were given. And this question is precisely the same as for any given 3 columns, can you find its orthogonal complement? So for any given 3 columns, and can you find orthogonal complement spanned by these 3 columns? So basically, you are supposed to find the orthogonal complement of the vector space spanned by these 3 columns, right? How can I do this? And there is very specific algorithm to find such an orthogonal complement. So let's do this. You know, I will begin from this system of these equations. Then in order to find the system of the equation, I will need to write down the so-called the augmented matrix. B1, B2, and B3. Taking the elementary law operations. So in order to find the solution, I will need to make this guy as an upper triangular matrix. Then I will get rid of this number. 1, -1, 0, 0, 1, -1, and 0, -1, and 1. And B1, B2, P1 plus B3. And now, also I have to get rid of this number 2. Then these 2 number equals to 0. And P1, P2, P3. Okay. Now, this system has a solution if and only if this guy equals to 0. Okay. So I have solution B1, B2, B3 equals to 0. But B1, this last equality can be written as 1, 1, 1. Let me rephrase this final equation. So for this system, I can find the solution if and only if the right-hand side column is orthogonal to 1, 1, 1. Right? That means orthogonal. Well, and so so I can find solution if and only if this guy is a member of the column space. And being able to the member of the column space is the same as orthogonal to this vector. So that means the orthogonal complement of the column space must be spanned by this guy. Okay. I really like this algorithm because no matter how many column vectors you were given, you can always find the spanning vectors of its orthogonal complement. Okay. So this is the end of today's lecture, and I will see you next time. And thank you for your patience.